going to be starting exams tonight. Here's the third on my docket, so I think that's what it is. Particularly speaking, it takes me a week to two to get the exam grades posted. Once I actually start, it doesn't take long. But you'll know when I'm done because the grades will post. As a general thumb, it takes me longer if you ask me when the exams will be graded. So they'll be done when they're done. So what are we doing today? Today's a fun day. Today's physics. We're going to look at motion in space. Let's say we're given a vector, our t, it's twice differentiable. And we're going to say that this represents the position of an object as a function of time. You know what velocity is? The velocity vector is just the rate of change of the position vector. Right, so v of t is dr dt. Acceleration is a rate of change of velocity. So A would be dv dt, or the second derivative of position. And then you have the speed, which is the magnitude of your velocity. Right? Remember, velocity and speed are not the same thing. Velocity also has a direction. Speed does not. So always some fun trivia questions. Acceleration. Do you know what the rate of change of acceleration is called? It's the jerk. Absolutely useless knowledge because you never use it in physics, but it is fun. Jerk has a rate of change. Called the snap. The snap has a rate of change. It's called the crackle. And the crackle has a rate of change. I want to take a guess on what the rate of change of crackle is. What was it? Pop. And that is not a joke. That is a real thing. Sadly, I don't think we have names for anything beyond that. There also happen to be names for things before position, because position is a rate of change. Take its antiderivative, you find what is the rate of change of. That has a name. I forget what it is. I have to look it up. But again, it's completely useless trivia knowledge because we never deal with that in physics. And a fun thought experiment, always fun to do. I'm assuming just about every one of you drive. How many accelerators does your car have?
One.
One?
Yeah.
disagree with one.
It's like variable, like the more you press, the more it changes.
Would it still be an accelerator, right?
Yeah.
It is not one. There's three. Remember, what is acceleration? Change in velocity, right? So your gas pedal definitely changes your velocity. Brake also changes your velocity, doesn't it? So it's an accelerator. Steering wheel changes your direction, doesn't it? Which would change your velocity. So it's an accelerator.
Well, isn't that, can't that be acceleration?
We don't call we call both acceleration and deceleration as just acceleration in physics. Because what is acceleration? It's a change in velocity, either increasing, decreasing in terms of magnitude, or direction. Plane of acceleration. Right? Acceleration vector of an object moving along a curve traced out by a twice differential function r lies in the plane formed by the unit tangent vector t and the unit normal vector n to c. Right? So you have an object moving along some curve. Find the unit tangent vector to that curve, the unit normal vector to that curve. They're guaranteed to be perpendicular, so they form a plane. Your acceleration lies in that plane. What's more, acceleration can be written in this component form. Derivative of speed times the unit tangent vector. Speed squared times curvature times the unit normal vector. Right? So, in other words, derivative of speed goes in the tangent direction. So the direction tangent to the curve. Speed squared times curvature, that component is in the normal direction. And so the direction that is normal to your curve.
Is that V prime with its vector?
No.
Okay.
If it was, then this wouldn't make sense. So then these are components of your acceleration. You have a component that goes in the tangent direction. Then you have a component that goes in the normal direction. These are called tangential and centripetal components of acceleration, or tangential acceleration and centripetal acceleration. And it can be shown. No, the tangential one's fairly simple. Tangential component always goes in the direction of motion. Right, so however your particle's moving, that direction is your tangential direction of acceleration. Same direction as motion. Centripetal always points to the center of the curve. It's the centripetal acceleration that keeps you from going straight. And if you take a turn, right, you're going around a curve, the car wants to keep going straight. That's why you kind of shift. If you turn too fast, you feel your body shift, because your body wants to keep going straight. And you're being forced not to. That's centripetal acceleration, combined with friction. If there was no friction, you'd be in a lot of trouble. There are two variables that affect how fast you can go around a curve. First is your distance from the center. So if you want to go faster around a curve, you increase your radius. So when you take an exit ramp, you want to go towards the out of the turn. The second factor is the bank, the friction. That's why a lot of turns are also banked. It allows you to go faster the greater the bank. Now, if these are the components, well, that's not, I guess, too terrible to find. Derivative of speed. And this is going to require us to find curvature, though. That's kind of interesting. So there are formulas. Tangential component, you could do acceleration dotted with the unit tangent vector. But again, that's kind of annoying because you have to find the tangent vector. You could also do V dot A over speed. Right? Velocity dot acceleration over speed. Then for your normal components, the centripetal component, A dot N. Again, that requires us to find the normal vector. The magnitude of velocity cross acceleration over speed. Or if you already happen to know your tangential component, the centripetal component is also the square root of the magnitude of acceleration squared minus that tangential component squared. And then you'd be able to write acceleration, again, as the tangential component times t plus the normal component times n. In this case, you would then think of t and n as your standard unit vectors for the plane of acceleration. Projectile motion. This is a fun one. Object in projectile motion can be modeled with the vector v naught t cosine of theta, v naught t sine of theta minus 1/2 gt squared, where v naught is the initial speed or the launch speed of the projectile. Theta is the angle with respect to the horizontal at which the projectile is launched. So you could call it your launch angle. And little g is acceleration due to gravity. What's the approximation for little g?
It's 9 point something. 9.8 something.
9.8 what?
9.8 meters per second.
Meters per second, or if we're dirty imperialists, 32 feet per second. Right, or 9.8 meters per second. There's a flaw with that. That is technically not a constant. Little g actually depends on your altitude, how far away from the center you are. The higher you go, the smaller it is. However, for most applications of everyday life, that change is so insignificant that you're not really going to notice. Just keep that in mind. Oh, and little g, of course, just is for on Earth. Right. Other planets have different accelerations due to gravity. That might be a model you want to write down and keep handy. Right, because chances are I'm not going to give it again. This is going to be one of those things where I'll ask a question about projectile motion, and you're expected to know that model. Centrifugal force exerted by a moving particle of weight W at a point in its path is given by W over G times A sub n. So weight over little g times the centripetal acceleration. Find centrifugal force exerted by a particle weighing 5 pounds at the ends of the major and minor axes as it traverses the elliptical path 20 cosine of t, 15 sine of t, where the magnitude of r is being measured in feet. So unfortunately, we're going to have to use the dirty empirical system. Unless you want to convert, which I don't, because it just makes it more hideous. So here's what I think I want to do first. So let's go ahead and plot that path. this new updated Mathematica. I'm gonna have to put this to the cloud. Cloud, actually, that's yeah, it's still running. That's really annoying. Right. There's our path. Major and minor axes. What's the major axis?
X,
What's the minor?
Y.
So we want the ends of these axes, right? This would be an end. Yeah. What's the value of t there?
Z,
Here's an end. What's the value of t?
Victory,
Here's an end. What's the value of t?
uh,
Here's an end. What's the value of t?
3, Victory.
Oh, look, and we're back, so we don't need to worry about that one. So the ends of the major axis will correspond to the values of 0 and pi. Ends of the minor axis will correspond to the values of pi over 2 and 3 pi over 2. Given weight is 5 pounds, right? We're going to use feet per 32 feet per second as our approximation for G. Which means the force we're looking for is a function of time. 5/32 times the centripetal acceleration is a function of time. Or 530 seconds, magnitude of V cross A over magnitude of B. Maybe I'll write that as actual magnitude. What's velocity?
Negative 20 sine t, 15 cosine t.
I don't have myself here. Then what's acceleration? What is their cross product? So before you actually do any work, what direction is the cross product going to be?
It's going to be orthogonal.
Hmm?
It's going to be orthogonal to that.
Which is what direction? Purely Z. Because both velocity and acceleration lie only in the xy plane. You take the cross product of that, you're going to get something that only goes in the z-axis. Means your first two components have to be 0. That makes your work a lot easier. Negative 20 times negative 15 is what? What is it? So you're going to have 300 sine squared minus negative 300 cosine squared, which is what? Way too large. 300 sine squared minus negative 300 cosine squared is what? 300 sine squared plus 300 cosine squared, which is just 300. What is that magnitude then? You shouldn't have to do any calculation. It's just 300. Now comes the fun one. What's the speed? Four hundred sine squared plus 225 cosine squared, all square root. And it's just the magnitude of velocity. What is 5 times 300? 1500, right? I think that can be simplified. I'll deal with that later. And 1500 over 32 can be simplified. They are both divisible by 4, at the very least. Are they both divisible by 8? So that'd be 8 on the denominator. What's 1500 over 4? What was it, 375? There's our function for centrifugal. For the ends of the major axis, we wanted f of 0 and f of pi, right? Well, again, just take a little time to think before doing calculations. At 0 and pi, what do you know about sine?
0.
What about cosine? But it's being squared. So cosine squared at the ends are going to be 1. Sine squared at the ends are going to be 0. Which means at both ends, your force is the same. Square root of 225 is 15. So now the question is, how does that simplify? 375 over 8 times 15. What was it? Not 23. 25. 25 eighths. What's the units? Foot pound is work. This is just force, right? So what's the unit? Just pounds. What does 25 over 8 turn into as a decimal? Because it's not repeating.
Three point 125.
Because it terminates, you could also write that. Yeah, but when in doubt, just leave it as an improper fraction. So again, before you just do the calculations, do a little bit of thought. Pi over 2, 3 pi over 2. Cosine 0. So cosine squared is 0. What about sine squared? Just 1. So again, your forces will be identical at those two endpoints. That is what you wind up with. Square root of 400 is 20. All right, so all we have to do is simplify 375 over 1600. What is it? No, I'm sorry, not 1600. 160, right? I was going to say, how about that? $375 over 160. What is it? 75 over what? 32. And units? And again, I think because 32 is a power, or 32 is a power of 2, that decimal does terminate. It's not repeating. What would that be in decimal form?
2.34375.
That's not 2, not 3, sorry. I agree. 2 point what?
34375.
Again, that's fine because the decimal terminates. Generally speaking, powers of 2 in the denominator do terminate. Right, because you can just keep dividing by 2, right? 1/2, 0.5, a quarter, 0.25, an eighth is 0.25 divided by 2. Right, so they'll constantly terminate. I don't know if any other decimals terminate. I know 3 doesn't. Which means any multiple of 3 is not going to. Or any power of 3, sorry, wouldn't. Does 12 terminate? I doubt it.
What about
10
10?
terminates, yeah. 10, 10, the powers of 10 are easy ones. 5, powers of 5 would terminate. To 7? This is 1/7. Is that a terminating decimal or is that a repeating decimal? Huh. Inquiring minds want to know. There you go, there's a challenge for you. Find the denominators that terminate. Okay, so projectile motion. We want to write the model in the form y equals f of x. So start with what we know. From that, we know that the x-coordinate would be v naught t cosine of theta, right? Solve for t. X over v naught times secant of theta. Right, just multiply both sides by 1 over v naught cosine. On the other hand, this model also tells us what y equals. Sure, you see where this is going. We just found what t is in terms of x. Replace that with the t and y, and then simplify. V naught over V naught. Well, that's easy. That's just one. X times, how would secant times sine simplify? What is it? It's tangent. How do I want to write this? This way. Okay, so we could write that. You could write it as a single fraction. But let's say I don't like two different trig functions. I want a single trig function. Secant squared. Tangent squared plus 1. I'm going to write a negative out in front. Could also write it that way. Again, theta is your launch angle, which means it's a constant. Sadly, I don't think that factors. I don't think that's binomial squared. It is not, which is unfortunate. Range. Range is just the total vertical distance. I'm sorry, total horizontal distance that is covered during the projectile motion. Let's say that's the projectile. That distance right there is your range. So it's just how far along the x-axis did the projectile travel. That's what we're looking for. Well, that means we'll need to determine the total time it takes the projectile to go from A to B, right? Since we can set our coordinate system any way we like, actually, I'm going to have to make an assumption. Here we're assuming that the launch is at the ground level. And if it's not ground level, there's going to be a slight adjustment that has to be made. So we're going to assume it starts at ground level and then goes obviously back to ground level. So y equals V naught t sine of theta minus a half gt squared, right? We want to find t. Well, its ending point is when it hits the ground, right? Is that equal to 0 and solve? You can factor out a t. So we get two solutions. T equals 0. Or t equals what? What is it? Two V naught sine theta over G. Our solution would then be the 2 V naught sine of theta over G, right? T equals 0 would indicate when the projectile was launched. So obviously we don't want that solution. Our range would be the x coordinate evaluated at that time, right? And x was v naught t cosine of theta. That was the x component, right? So you just evaluate that expression when t is 2 v naught sine theta over g. That's what we would get, right? Write that using only one trig function. How could you write that with a single trig function? What identity are we going to have to use? We don't remember a trig. That's sad. Two sine cosine is sine of 2 theta. Double angle identity for sine. So v naught squared sine of 2 theta all over g. That is the range of a projectile. Again, assuming that it launches at ground. I'll leave it for you to derive what happens if it launches at an initial height. H, call it. That might make a good exam question. I think that should be fine. I should be able to finish it up on Thursday and then start the next topic. So don't forget, homework 9 due Thursday. Homework 10. I don't remember when I started posting them earlier. You may see 10th homework assigned now. That won't be due until the 4th of March, though, because I finished up on Thursday. And you have your second project due this week as well, right? It's due Friday, which is a fun project, approving Kepler's laws. We will finish this up on Thursday and then start multivariate functions. So I'll see you all on Thursday.